The glenohumeral joint is composed of the humerus and scapula and is the most mobile joint in the body. The motion of the humerus relative to the articular surface of the scapula, the glenoid, is described as spinning, sliding, and rolling. Shoulder motion and stability is achieved via the coordinated contraction of the deltoid and rotator cuff. The deltoid is the largest muscle in the shoulder. It elevates the arm. The deltoid consists of 3 distinct heads: anterior, middle, and the posterior. The middle deltoid wraps around the greater tuberosity to generate a stabilizing compressive force. The rotator cuff is composed of 4 muscles that generate the torque necessary for rotation. The anatomic arrangement of these muscles generates humeral head compression and glenoid centering at all joint positions. Muscles generate forces that are converted to torques in proportion to the perpendicular distance between the joint center of rotation and the muscle's line of action. This distance is the muscle's moment arm. The larger the moment arm, the greater capacity for that muscle to generate the torque required for motion and support external loads. The location of the moment arm relative to the center of rotation determines the type of motion the muscle creates. Shoulder muscles with lines of action superior lateral to the center of rotation generate abduction. Lines of action inferior medial to the center of rotation generate adduction. Lines of action anterior to the center of rotation generate internal rotation. And lines of action posterior to the center of rotation generate external rotation. Rotator cuff tears have negative consequences on motion and stability. As the rotator cuff fails to balance the deltoid, the humeral head migrates superiorly and impinges with the acromion, leading to further tearing. Dr. Charles Neer coined the term cuff tear arthropathy, or CTA, to describe this arthritic, eroded condition of the glenohumeral joint following prolonged subacromial compression. The standard of care for CTA is reverse shoulder arthroplasty. The reverse shoulder prosthesis inverts the anatomic articulation, making the glenoid convex and the humerus concave. Inverting the concavities restores stability by creating a fixed fulcrum that prevents superior migration, facilitates the deltoid to elevate the arm, and limits motion to only spinning. Inverting the concavities also causes an inferior medial shift in the center of rotation and position of the humerus. This dramatically alters the relationship of each muscle relative to its normal physiologic function. Medially shifting the center of rotation increases the length of the deltoid abduction moment arms, improving its efficiency to elevate the arm. However, medially shifting the humerus shortens the rotator cuff muscles, which has negative consequences on rotational strength and motion, and leads to impingement of the humerus with the scapular neck, known as scapular notching. Inferiorly shifting the center of rotation and humerus elongates the deltoid. Deltoid elongation improves muscle tone and has been suggested to increase strength and joint stability. However, deltoid elongation modifies the normal contour, decreases wrapping around the greater tuberosity, and creates cosmetic concerns. Excessive deltoid elongation may lead to acromial stress fractures. Inferiorly shifting the humerus alters the subscapularis and infraspinatus line of action, increasing their adduction capability at low elevations, counteracting the work of the deltoid. Different prosthesis design parameters impact how the center of rotation and position of the humerus change relative to the anatomic shoulder. The Grammont reverse shoulder glenosphere, whose thickness is 1/2 its diameter, medializes the center of rotation to the face of the glenoid to minimize the torque on the glenoid bone implant interface and increase the deltoid abductor moment arm lengths. The Grammont humeral prosthesis has a 155-degree humeral neck angle and is placed within the humerus, causing it to shift medially and be placed directly inferior to the glenosphere, which elongates the deltoid but shortens the rotator cuff. This implant design and resulting humeral positioning is effective at restoring active abduction and forward flexion, but is less effective at restoring active rotation. Grammont's medial positioning is also responsible for a low glenoid loosening rate, but a high scapular notching rate. Prosthesis designs that lateralize the center of rotation relative to the Grammont may improve active rotation, strength, and stability, and also reduce the scapular notching rate. Lateralizing the center of rotation lateralizes the humerus, which tensions the remaining rotator cuff muscles and minimizes humeral impingement with the scapular neck. However, lateralizing the center of rotation increases the torque on the glenoid fixation surface and decreases the length of the deltoid abductor moment arms. Because the deltoid moment arms are decreased as the center of rotation is lateralized, the deltoid becomes less efficient and requires a greater force to elevate the arm. These elevated loads have negative implications on rehabilitation, muscle fatigue, stress fractures, and prosthesis fixation. Alternative prosthesis designs are available that lateralize the humerus without lateralizing the center of rotation. Doing so better restores rotator cuff muscle tension while maintaining Grammont's deltoid moment arm lengths and minimizing the torque on the glenoid implant bone interface. The humerus can be lateralized to also minimize scapular notching by decreasing the Grammont humeral neck angle of 155 degrees, proportionally increasing the Grammont glenosphere diameter and thickness of 36 by 18 millimeters, decreasing the humeral liner constraint, and by increasing the medial offset of the humeral prosthesis. Increasing the humeral liner stem offset increases the deltoid abductor moment arm lengths to improve joint efficiency and increases deltoid wrapping to improve stability. Next-generation implant systems achieve this increased offset by placing the liner on top of the resected surface instead of within the humerus. Doing so permits the same humeral stem for both anatomic and reverse shoulder arthroplasty, improving the ease of revisions and reducing the overall cost by retaining the same implant. Repair of the subscapularis with anatomic shoulder arthroplasty is critical. Restoring the transverse force couple created by the subscapularis and posterior rotator cuff is essential for stability. However, the combined force generated by these opposing muscles increases the joint reaction force. With reverse shoulder arthroplasty, as the subscapularis functions as an adductor, its line of action opposes the deltoid, requiring the deltoid to work more for a given motion when the subscapularis is repaired. However, subscapularis repair may not be necessary for stability for alternative prosthesis designs that lateralize the humerus more. Thus, recommendations for subscapularis repair are not universally applicable to all reverse shoulder designs. The requirement for repair is dependent upon humeral positioning. Not repairing the subscapularis with lateralized humeral designs may reduce the force required by the deltoid and reduce the overall joint reaction force, since the subscapularis no longer functions as an adductor. Glenoid implant positioning alters reverse shoulder biomechanics. Inferior glenoid placement is recommended to achieve glenosphere overhang and avoid scapular notching. However, inferior glenoid placement further shifts the center of rotation and position of the humerus. This further elongates the deltoid, reduces deltoid wrapping, and may also increase the risk of acromial stress fractures. Using reverse shoulders in eroded glenoids medializes the joint line, further shortens the rotator cuff, and further reduces deltoid wrapping. Excessive joint medialization can completely eliminate deltoid wrapping and cause the deltoid to generate a distraction force. When using reverse shoulders in medially worn glenoids, the joint line should be lateralized with bone graft or by using thicker glenospheres. When using reverse shoulders in superiorly worn glenoids, the joint line should be lateralized with superior augmented implants. When using reverse shoulders in posteriorly worn glenoids, the joint line should be lateralized with posterior augmented implants.